In the last few lectures, we explored the notions of removable singularity and the pole of a function f at z0 in great detail given an isolated singularity z0. We also studied the behavior of the function as we approached these isolated singularity. So, for example, when we approach a removable singularity, we notice that the limit should exist, and when we approach a pole of a function f at z0, then we notice that the absolute value of the function should blow up. We also explored Laurent series expansion of a function defined on an annulus, and we classified our singularities based on how the negative coefficients of the Laurent series behave. However, we have still not really looked into what happens when a given isolated singularity is an essential singularity and how the function behaves as we approach an essential singularity. We already have seen that when we looked at the function, if you recall that f of z is equal to e to the power 1 by 1 minus z is a function which has an essential singularity at 1, z0 equal to 1. And we did check that if you pick the sequence carefully, then f of zn converges to 1 and f of zn prime, that is what we had picked the second sequence, f of zn prime converges to I. So, we will now prove a result which tells us that in fact the essential singularities are quite bad in that sense, that the behavior can get as bad as one can expect. Let me write down the statement of what will be proved now. This is called the Casorati Weierstrass theorem. So, let me just complete what I was writing. Then for the Zn right sequence, I think it was 1 minus 1 by 2 pi I n. F of Zn converges to 1. In fact, f of Zn is equal to 1 for each of these. And for Zn prime, this is equal, if this is 1 minus 1 by 2 pi I n plus I pi by 2, f of Zn prime converges to I. So, there is no one limit that we will be able to get hold of in these cases. Let me now state the Casorati Weierstrass theorem. Casorati Weierstrass theorem basically tells us that you pick any complex number alpha, then we can get hold of a sequence Zn converging to the essential singularity Z0 such that f of Zn converges to alpha. Let me write that down. Let Z0 be an essential singularity. Recall that it's an essential singularity and hence it's neither a removable singularity nor a pole. So, of a function f. Then given alpha in the complex plane, there exists a sequence Zn in dz0 r minus z0 such that Zn converges to Z0 and f of Zn converges to alpha. Let us give a proof of the Casorati Weierstrass theorem. The proof is going to be by contradiction. Suppose we have a complex number alpha which does not satisfy the conclusion of Casorati Weierstrass theorem. Suppose alpha be such that there does not exist Zn converging to Z0 where and f of Zn converges to alpha. Suppose there does not exist any such sequence. What does that mean? This means that i.e. there exists an epsilon positive such that if you look at the disk of radius epsilon around alpha, then there is no point of dz0 r minus z0 which gets mapped by f to this disk. Let me just write that down. There exists an epsilon positive such that d alpha epsilon intersected with f of dz0 r minus z0 is empty, right? And hence if you consider the function, let's call it g of z is equal to f of z minus alpha, then g is a function which does not vanish. And g does not vanish on dz0 r minus z0. We do not have a function, we do not have a 0 of the function g in dz0 r minus z0. Because this function does not vanish here, let's invert it and let's define what was taken here. G was taken, I guess. So let's define h of z to be equal to 1 by g of z. And if you notice, h is holomorphic on dz0 r minus z0. Now let's explore what type of a singularity z0 is to h. Notice that h is defined on dz0 r minus z0. In particular, z0 is an isolated singularity of h as well. So the first observation that we would like to make is the following. If you look at f of z minus alpha, by our very assumption, the absolute value of g of z, this has to be greater than epsilon. Why? Because we have obtained an epsilon such that the image of f or image of dz0 r minus z0 under f does not intersect d alpha epsilon. Therefore, any point here, any point f of z will be outside the disk of radius epsilon around z0, around alpha, and therefore the absolute value of f of z minus alpha should be greater than epsilon, right? And this tells us that 1 by g of z, absolute value of that, which is basically absolute value of h of z, this is less than 1 by epsilon on dz0 r minus z0. But what does that mean? This means that h is bounded on dz0 r minus z0. Now we are in the perfect setting to apply Riemann removable singularity theorem, and we can conclude that z0 is a removable singularity of h by the Riemann removable singularity theorem. Z0 is a removable singularity. Of h. So in particular, h is a function now which can be thought of as a holomorphic function in a neighborhood of z0. So the key thing to note right now is that being the inverse of 1 by g of z, where g of z is not a constant function, h is not a constant function. In particular, h is not the 0 function, and it can happen that z0 is a 0 of h. So we will just write h of z to be equal to z minus z0 to the power m times h1 of z, just to ensure that m is greater than or equal to 0. If at all it vanishes at z0, we will just capture the power to which it vanishes and such that h1 of z0 is not equal to 0. So by going down to a smaller neighborhood if needed on dz0 r prime, I will not call the smaller neighborhood anything else, let me just call it z0 itself, and I'll just say that on dz0 r we then have, what was h of z? H of z was basically 1 by g of z. Just go up and see what it was. And what was g of z? G of z was just f of z minus alpha, right? So let me just write that down. We have 1 by f of z minus alpha is what is written as z minus z0 to the power m times h1 of z and therefore f of z is going to be equal to 1 by h1 of z, which is a holomorphic function because it doesn't vanish. We may assume that h1 of z is not equal to 0. That we can always do by shrinking our neighborhood if needed. So here we can talk about 1 by h1 of z, which is a holomorphic function, by z0, z minus z0 to the power m plus alpha. So this is going to be alpha plus this. Therefore, we get to conclude that this is the exact expression of a pole, right? This tells us that f has a pole of order m at z0. But that's a contradiction because we started off with z0 being an essential singularity. That's the very hypothesis, right? Z0 is an essential singularity of the function f. In particular, it's neither a removable singularity nor a pole. The fact that we have concluded that it is a pole tells us that there is something wrong with the assumption. And so our assumption has to be wrong. Therefore, there exists a sequence. Hence, there exists a sequence Zn converging to Z0 such that f of Zn converges to alpha. What we have effectively proved is that the image f of under the image of dz0r under f is dense in C. So the Casorati Weierstrass theorem gives us some amount of idea about how a function behaves as we approach one of its essential singularities. Let us now move on. Let's now define what is meant by a meromorphic function. But before we do that, let's recall the notion of the order of a pole of a function f at a point z0. So suppose we start off with a function f and let z0 be a pole of order m at z0. What does that mean? That means that f of z is equal to g of z by z minus z0 to the power m in dz0 r minus z0, where g is some holomorphic function there. G is holomorphic on dz0 r, and we also ensured that g of z0 is not equal to 0. If you go back a couple of lectures and look at how we got hold of the singular part of a function having a pole at z0, you will get hold of what our function g is. Right, so there is this number m which is being called as the order of the pole at z0 of f. We will define a similar notion of the order of a 0 of a holomorphic function which vanishes at a point z0. So suppose we have in fact used this number multiple times. This is sometimes also called as the multiplicity of the 0. Suppose z0 be a point such that f is holomorphic in a neighborhood of 0, in a neighborhood of z0, and such that f of z0 is equal to 0. Let's put an extra condition of non-constant. Be a non-constant holomorphic function defined in a neighborhood of z0 such that f of z0 is equal to 0. If the function is non-constant, then the principle of analytic continuation tells us that all derivatives cannot be equal to 0, because if all derivatives are 0, then the coefficients of the power series expansion around z0 will be forced to be equal to 0, and therefore the function will turn out to be identically equal to 0 in. So this is not just necessarily restricted to when our function f is defined in a neighborhood of 0. Suppose f is defined in some domain omega which contains z0, we still can conclude all these things. And by the factorization theorem and principle of analytic continuation together, we will be able to hence conclude that f of z can be written as z minus z0 to the power m into g of z, where g is also a holomorphic function in a neighborhood of z0 and g of z0 is not equal to 0. So just being consistent with the notion of order above, we will just then say that f has a 0 of order m at z0. All right, let's now keep these things in mind, and let's now try defining what is meant by a meromorphic function. To define a meromorphic function, we don't need to really have these jargons, but anyway, they are needed to describe what follows. Let me now define what is meant by a meromorphic function. We will stick to open connected subsets in this lecture from now on. So let omega be an open connected subset. And let S be contained in omega be a subset. Of omega. And suppose we have a function f which is defined on omega minus s be holomorphic on omega minus s. We then say that f is a meromorphic function on omega. Notice the terminology. We say that f is a meromorphic function on omega. Let me just underline what we have just defined. If the following two conditions are satisfied. S is a discrete set, is a discrete subset. What does that mean? It means that if Z0 is some point in the set capital S, then there exists some neighborhood dZ0R such that dZ0R is contained in omega, and such that dZ0R intersected with S is going to give you back Z0. And what about the behavior of f at the points S? The second condition is that f has either a removable singularity at the points of S or a pole. So f has either a removable singularity or a pole at points of S. So if these two conditions are satisfied, then we say that f is a meromorphic function on omega. So notice that if z0 is a point where z0 is a point in capital S where f has a removable singularity, effectively we can define f across the point z0. It extends to z0 as well. So the poles is where we will not be able to extend it, but we know that as we approach the pole, the absolute value blows up. So meromorphic functions are the best classes of, it's in more general in some sense to holomorphic functions. We will now define an equivalence of meromorphic functions. Note that there is some capital S lurking in the background. So let me just note an equivalence there. We say that f is two meromorphic functions f and g on omega are equivalent if f is from omega minus s1 to c and g is omega minus s2 to c satisfies f of z is equal to g of z on omega minus s1 union s2. So I'll give you an exercise here. You should sit down and check that if S1 is a discrete set and S2 is a discrete set, S1 union S2 is a discrete subset of omega if S1 and S2 are. And therefore, the equivalence relation is effectively telling us that you look at omega minus S1 union S2, then the function f and g are the same there. So now that we have defined an equivalence relation, I will allow you to again sit down and check that this is indeed an equivalence relation. That's also an exercise for you, and define a set M of omega to be the set of all equivalence classes of meromorphic functions on omega. Meromorphic functions on omega. And the equivalence is exactly how it is defined here. Now, if you have two equivalence classes, let's now define how to add these equivalence classes. So even though they are being called equivalence classes, they are just meromorphic functions. They are just functions which are defined outside a singular set. Notice that S is being used for the singular set, or S is being used because it's the set of singular points. So if we take f comma g in M of omega, their equivalence classes define f plus g. So that means that i.e. there exists a function f on omega minus s1 to c, and f, not f1, f and g from omega minus s2 to c, which represent f and g respectively, and define f plus g to be the equivalence class of the function f plus g, which is defined on omega minus s1 union s2 into c. There are a few checks to be done here. The first check is that f plus g is indeed a meromorphic function, and secondly, this definition is well defined. I will not indulge into proving. They are quite straightforward. It's easy to see that the sum of these equivalence classes is well defined. Similarly, we could define f times g to be the equivalence class of, so here f plus g basically means f of z plus g of z. So the standard addition of functions f plus g of z is equal to f of z plus g of z. And how about this? This is a map from omega minus s1 union s2 to c, again given by the usual multiplication of functions. So this is going to be fg of z is equal to f of z times g of z. The check that f times g will turn out to be a meromorphic function is quite straightforward. There are many cases that will come up. One just has to sit down and check them. I will anyway do it for f times g and leave f plus g as an exercise for you. So the claim is that z0 be a point in s1 union s2, then z0 is either removable singularity of f times g or a pole of f times g. The first thing to note is that because s1 and s2 are both discrete, an exercise earlier tells us that s1 union s2 is also discrete. So that is already taken care of. We just have to look at whether it is a removable singularity or a pole of f times. We know what is the behavior of our functions f and g in a neighborhood of z0, right? We know that now that we have written an order of the 0 and the pole, we can still write this function f of z as being equal to z minus z0 to the power m times f1 of z, where f1 of z0 is not equal to 0 and m is a positive or a non-negative number, or rather non-negative and is either non-negative or negative based on whether z0 is a removable singularity of f or it's a pole of f. Z0 is a 0 or a pole. Let me put it that way. In fact, m is equal to 0 is allowed. In that case, z0 is considered to be a 0 of order 0. That is also allowed. And what will happen to g of z? G of z is going to be equal to g, this is m1, let's call it m1, and let's call the second one m2, g1 of z, where g1 of z0 is not equal to 0. So notice that I have tried to capture all the cases by writing f and g in this manner, because if, say for example, z0 was in S1, that means that it is a singularity of f, isolated singularity of f. It could happen that z0 is a removable singularity or a pole. If it was a removable singularity, then we can extend our f past z0 as a holomorphic function, and based on whether it is a 0 or not, our m1 will be either 0 or greater than 0. If it is having a 0 at z0, then m1 will be greater than 0, and if it is not 0 at z0, then m1 would be equal to 0. That is the case when z0 is in S1. Similarly, z0 if in S2 will tell us that, oh, by the way, what happens if z0 was a pole? Then we could have written f of z as f1 of z by z minus z0 to the power m, where m is the order of the pole. And in that case, our m1 would turn out to be a negative number. So that is what is being written here, as either m is non-negative or it is negative, based on whether it is a removable singularity, or rather whether it is a 0 or whether it is a pole. A very similar argument tells us that we can write g in this manner, and therefore f of z times g of z is going to be equal to z minus z0 to the power m1 plus m2 times f1 of z times g1 of z, which tells us that f times g will either have a pole or it will have a removable singularity, based on whether m1 plus m2 is negative or whether m1 plus m2 is positive. So based on non-negative, based on that, our behavior of z0 will be either a pole or a removable singularity. So I'm trying to squeeze in all the cases here. You should actually sit down and think about what are the various cases that are being considered to conclude that the point z0 is either a removable singularity or a pole. It cannot be an essential singularity because of the behavior of the function f in a neighborhood of z0 and the function g in a neighborhood of z0. A very similar argument wherein you take all the cases here will tell us that the points of S1 union S2 are going to be either removable singularities of f plus g, or it is going to be a pole of f plus g. Okay, so that is good, because I'm going to write down now a proposition which tells us that with these operations, we just define two operations, right? You take any two elements in oh yeah, there is one more exercise which actually needs to be done of well-definedness. That's quite straightforward. I will not do it and spend time here. Rather, let me give a statement which tells us that with these operations of addition and multiplication, the space of meromorphic functions is going to be a field. The space of meromorphic functions m of omega is a field with the operations defined above. I'll not prove all the properties needed to check that with these operations it's a field. Let me just make one comment uh, that if you take a function f, which is a meromorphic function on omega, then 1 by f is also going to be a meromorphic function. So the only thing that needs some work is this particular claim. So let f be in m of omega, then define g of z to be equal to 1 by f of z, where, so what is the meaning of f is in 1 of, so let me not rush. Then f is a map from omega minus s into C, where S is a singular set where the function f can have either a removable singularity or a pole. Now let S1 be the set of all those points z in C such that f of z is equal to 0. That is what our S1 is. The first point here is to note that S1 is going to be a discrete set. Let f be in n omega star. It means f is non-zero. Non-zero holomorphic function on omega minus s. So that means that the zeros are going to be discrete by the identity theorem. By identity theorem, S1 hence is a discrete set. S1 is discrete, and therefore S1 union S2 is discrete. Sorry, S union S1 is discrete. Define a function g on omega minus S union S1 into C by g of z is equal to 1 by f of z. Notice that on omega minus S1 union S, the function f does not vanish because all zeros of f are captured in S1. And therefore, g of z equal to 1 by f of z is an honest holomorphic function on omega minus S1 union S. Now the question comes about what happens at the points in S1 union S. So let's just address them one by one. Let Z0 be a point in capital S. What does that mean? That means that Z0, f of Z0 is equal to 0, and because it's a non-zero function, we can write f of z to be equal to z minus Z0 to the power m times g of z, where g of Z0 is not equal to 0. And therefore, in a disk, punctured disk rather, around z0, what can we say? We can say that 1 by f of z is going to be equal to 1 by g of z. So this r is picked so that it is having only z0 from the set S, and g does not vanish on the z0 r minus z0. Both these conditions are being imposed. By shrinking if needed, we can assume that this is the case. And 1 by f of z, by manipulating this, is going to be 1 by g of z by z minus z0 to the power n, which tells us that 1 by f has a pole of order m, where m is the order of the 0 of f at z0. So for every point in capital S, that's going to be a pole of the function 1 by f. That's a good observation to keep in mind. And if z0 is a point in capital S to begin with, so this was S1 or S, what did I pick? So I was actually picking S1, I guess, because S1 is the set of all points where the function f vanishes. So this is basically S1 that the point is being picked from. Now let's pick a point in capital S. Capital S to begin with was either a removable singularity or a pole. If Z0 is a pole of f, what does that mean? That means that in a neighborhood, f of z is going to be equal to some g of z by z minus z0 to the power m in some neighborhood d z0 r minus z0, where r is small enough so that g does not vanish here, and therefore we can write 1 by f of z to be equal to z minus z0 to the power m times 1 by g of z. So let's assume here that g is not equal to 0 on dz0 r minus z0. We can always assume this by shrinking our r if needed, and therefore this tells us that 1 by f has a removable singularity. In fact, it has a 0 of order m at z0. That is precisely what we can get to conclude by looking at this. What about if f has a removable singularity? I'll leave that as an exercise. Check that if z0 is a removable singularity, then either it will be a removable singularity or a pole of f is either a removable singularity in the case when f of z0 is not equal to 0 after extending it to z0, or a pole of 1 by f. If f of z0 is equal to z0, then z0 is going to be a pole of 1 by f. I'll leave the remaining things as a simple exercise for you to sit down and check. It's going to give you better insights into the notion of meromorphic functions. Let me give you a definition of the order of a function f at z naught, and stop by giving a few of its properties. Let me now define the order of a function, order of a meromorphic function. At a point z naught. So let f be meromorphic on omega. Again, recall that this means that f is holomorphic on omega minus capital S, where capital S is a discrete subset of omega, and every point of capital S is either a removable singularity of f or a pole of f. So here f being meromorphic means exactly that. That's what we had defined some time back. Then for z0 in omega, define the order of f at z naught to be if z0 is in capital S and z0 is a removable singularity. Suppose this is the case we are in. It can happen that z0 is in capital S because z0 is taken to be some arbitrary point in omega. Then order of f at z0 is equal to the order of the 0 at z0 of f. What does that mean? That means we can write f of z as being equal to z minus z0 to the power m times g of z, where g does not vanish. And it can happen that m is equal to 0, and this m is what is called as the order of f at z0, i.e. order of f at z0 is equal to m. M is just non-negative. That's what you should remember. What about when z0 is in S and z0 is a pole of order m? Then we define the order of f at z0 to be equal to m minus m. Remember that if it is a pole, then we can write f of z as g of z by z minus z0 to the power m, where g of z0 is not equal to 0. And this m is what was the order of the pole. So the order here is now order of the function f at z0 is being defined as minus m in this particular case. If z0 is now not a point in capital S, then yet again follow 1. And we will be able to define the order of f at the point z naught. And finally, if f is identically equal to 0, then the order of f at z naught is defined to be infinite. This is how we define the order of the function f at the point z naught. Let me now give you a couple of exercises which captures some of the properties of this order function. So odd at z0 is now going to be a function from m of omega. It takes a meromorphic function and it gives you the order of f at z0. It's going to map you into z, and odd satisfies the following. odd of f times g at z0. So there are a few things which I have pulled under the rug, namely that to talk about order of f for uh, f in M of omega, one should be able to say that this order is well defined on an equivalence class. That's a very, very simple check. That's the reason why it's not being explicitly spelled out. But nevertheless, one should keep in mind that now we are defining this function on M of omega, which basically is an equivalence class of meromorphic functions. And the property that is to be checked is that order of fg at the point z0 is going to be order of f at z0 plus the order of g at z0. And how about the order of f plus g at z0? That's going to be greater than or equal to the minimum of order of f at z0 and the order of g at z0. If order of f at z0 is not equal to order of g at z0, then this inequality will be an inequality. If it is equal, then it could happen that the inequality is strict. Anyway, these are interesting exercises to sit down and check. The reason why all this was done is to capture the idea that the function order is what is called as a valuation on the field of meromorphic functions.